Our previous notes have focused on a situation where we basically observed information from a homogeneous population. And we were interested in estimating an overall probability of success or overall success prevalence. Now we're going to look at a situation where our items in our population come from one of two different groups. And we're going to be interested in estimating let's say the probability of success for group 1 and the probability of success for group 2, and then make some comparisons. Since we have two groups and a binary response, we're going to summarize our data that we get in a 2x2 contingency table format. To help motivate this further, here are some examples that we will be looking at. So this first one deals with Larry Bird. Larry Bird is often thought of as one of the greatest basketball players of all time. And what I have here is some data from him playing basketball in NBA games corresponding to his free throw shooting. Now, since Larry Bird is thought as one of the greatest players of all time, he happens to also be one of the best free throw shooters of all time. Now, the free throw shooting data that I have here corresponds to free throws that are done, two free throws done consecutively. If you're not a basketball fan, that's okay. Just make sure you realize that in most occasions, free throws are shot in pairs. So you have one shot and then you have another shot right after that. These shots are not, let's say, impeded in any way by any other player. They are shot, you could say, freely from about 10 feet from the basket. Now, there are other occasions where free throws are shot just, let's say, maybe in three at a time, or maybe just one. We're just going to look at the situation that occurs most often where free throws are shot in pairs, where two shots are done consecutively. So here's the data that we have summarized in a 2x2 contingency table. So this 251 here represents on his first free throw, he made it, and on his second free throw, shot right after it, he made it as well. 34 times he made the first, but then missed the second. 5 times he actually missed them both. Let me do some erasing here. Now, we get the name 2x2 contingency table because we see we have two rows and two columns in terms of what I just highlighted there. Now, outside of those two rows and two columns, we have another column, we have another row. Those are often referred to as margins in a contingency table. And what they do is they summarize information across one of the other, let's say, variables. So, for example, this 285 here represents that Larry Bird made 285 first free throw attempts where I don't care about what happened on the second attempt. And so all it is 251 plus 350 plus 34. Again, let me do some erasing. And lastly here, this 299 represents that 299 times he made the second free throw where we don't care about what happened on the first attempt. There are a total of 338 free throw pairs that were shot together. So what I circled there, if you add that up, you get the 338. Now, in this particular situation, what kinds of questions are we interested in? If you're a basketball fan, probably the number one thing that you're interested in is, given Larry Bird, let's say, made the first free throw or made the second free throw, what's the probability he's going to make? I'm sorry, let me restate that to make sure I get it right. It's easy to misspeak here. Given Larry Bird, let's say, made the first free throw, or given that he missed the first free throw, what's the probability that he's going to make the second free throw? If you're a basketball fan, in some kind of intuitive sense, you might think that for just a regular old basketball player, if you miss that first free throw, you might get down on yourself. You're kind of sad that you missed that first free throw, and that might affect negatively then the ability to make that second free throw. So in other words, the probability of success on that second free throw is going to be dependent upon what happened on that first free throw. Intuitively, as a basketball fan, you might think that. So using this observed data that we have in the sample, we can use statistical methods in this section to check to see if that is actually true. Another sports example actually comes from my very first paper that I ever had published. And it deals with field goal kicking again. And in this particular situation, again, for a field goal result, we either can have a success or we can have a failure. And if you're a football fan, you know that field goal kickers tend to prefer to kick inside dome stadiums rather than in an outdoor stadium. Why? Well, because in an outdoor stadium, the weather can affect the field goal attempt. You know, there might be some wind involved, there might be rain, there might be snow, and those kinds of conditions might, let's say, lower the probability of success as opposed to kicking inside a dome stadium where you would think these are the perfect conditions to kick under. And so again, in this kind of in the methods that we're going to be talking about in this section, we're going to be able to compare the probability of success over these two groups and make a judgment of, are they the same? Are they different? If they are different, how much are they different? And lastly, an example that doesn't deal with sports is something that was very important, and that is dealing with the COVID-19 vaccine. So back in 2020, it was often headline news towards the end of the year about, well, we have these vaccine clinical trials going on. Is the vaccine preventing infection from the disease, or from the virus that causes the disease, I should say? And so the very first vaccine that was approved is often referred to as the Pfizer vaccine, because that was one of the companies that was involved in developing it. And so in this particular case, a person is either positive or they are negative for the disease during this certain period of time that people were observed in this clinical trial. And of the 34,922 people that participated in this clinical trial, about half of them received the vaccine and half of them received the placebo, where the people that were involved did not know if they received one or the other. Just in case you're not familiar with the term placebo, basically means that you're not actually given an active drug through the administration of a shot. So it might be just saline solution that they inject in you. So what we have here in this particular, and this is the actual results from the clinical trial, 8 people received the vaccine within a period of a few months, still came down with the virus. They were positive for it. But 17,403 were not. For those in the placebo group, 162 were positive, where 17,349 remained negative, meaning they didn't get the disease. So, given this kind of data then, we're very interested in measuring, does the vaccine help prevent infection from the virus? What is the vaccine effectiveness? And so we'll be looking at that later in the notes. So right now we're going to be focusing on these 2x2 contingency tables. Later we will be looking at larger contingency tables. Okay, so let's take a look at our notation here and put some probability distribution or probability modeling system with respect to the kind of data that we're going to observe. So previously we've seen a situation where we had, let's say, y1 through yn as binary responses, and they had a Bernoulli distribution with a probability of success parameter pi. We have exactly the same setup here, except now we have information for group 1, we have information for group 2. So all I'm going to do is use exactly the same notation where I have a group 1 and I have a group 2. So we have a second subscript. Our sample, this is actually a little bit of a typo there. our sample is going to be a sample size of N1 from group 1, a sample size of N2 from group 2. Then similar to what we had previously, if we were to, let's say, sum all these all these y's, we get W, which is the number of successes out of a certain sample size or certain number of trials. Excuse me. Same thing here, but now I'm going to put a subscript with respect to the W so we can denote the corresponding group number. So W sub j, so where j is equal to 1 or 2, represents the number of successes for group J. It has a binomial distribution associated with it, with a probability of success parameter of pi sub j and n sub j trials. Now W1 is independent of W2. For that reason, people often refer to this as independent binomial sampling. Okay, so what does that mean in a practical sense? Well, if we take a look at, let me do some erasing here. If we take a look at our vaccine data here, what that says is all the people that are in the vaccine group do not have an effect on all the people in the placebo group in terms of becoming positive or negative. Depending upon how the clinical trial is done, that seems to be a reasonable assumption that if I receive the vaccine and somebody, let's say in maybe New York City, receives the vaccine, if I get the disease or not, it's not going to affect if that person gets the disease or not. Of course, we know that people interact with one another, so there is a limited possibility that indeed, if I come down with a disease, I might infect somebody who's also participating in the clinical trial. So this is an example of where we have these particular probability models and we have certain assumptions about them, and we can feel reasonably good about that. These assumptions are reasonably satisfied, but we know that there is a small chance that they're not completely satisfied. Okay. Now the maximum likelihood estimate then for pi sub j ends up being pi hat sub j. It's what you would expect, the number of successes observed for group J divided by the number of trials for group J. One last little notation bit here. It's very common in categorical data analysis and other places as well to use a plus in a subscript to mean that you are summing over something. So for example, to form W sub j, I needed to sum over the I subscript, that first subscript, which represents the item, let's say number, for that particular group. And so if I say y sub plus j, that's equivalent to y sub j. And we can use the plus subscript in other areas as well. Okay. So here's a contingency table then that basically puts our notation in it. So given that you're in group 1, the number of people with response level 1, maybe like a success, is observed to be W1. Given that you're in group 1, the number of people or number of items that have response 2, maybe like a failure, is N1 minus W1. And you can see how some of these plus subscripts are being used here. So if I add across all the W's there, I get W plus. Now we could also write the table in terms of these probabilities associated with the distribution for W. The probability of success, you could say. So if I let 1 be success, 2 be failure, then pi sub 1 is the probability of success given that you're in group 1. Pi sub 2 is the probability of success given that you're in group 2. So notice then, of course, if you have a success, you could have a failure, so that probability 1 minus that pi. If I were to sum up these probabilities, of course, I would get 1. So how would you actually, let's say, simulate observations in this particular setting? Well, you use exactly what we saw from section 1. You could use one binomial distribution for group 1 and one for group 2. Okay, so let's take a look at how we can get this contingency table data into R. So let me bring up 10 again. Okay, so we're going to be working with the Larry Bird data. So my corresponding program is called bird.r. And I'm going to create the contingency table, and I'm going to put the information object called c.table, for the lack of a better name, C for contingency. To form the contingency table, we use a function called array. In array, an argument is data. This is where we put our corresponding data. And so what I'm going to do is combine together all those numerical values that were in the 2 by 2 portion of our table. And the way that I combine them is very important. Let me bring up my notes here. So if I go all the way back to the data, the order that you see these counts entered into that C function corresponds to I order it by column. So I put 251 first, then 48, then next I put 34, and then 5. So let's go back. So you can see definitely I have that ordering there. Next I need to tell R, well, how big is the table? And that's where dim for dimension is put in there. And I combine together 2 and 2. 2 rows, 2 columns. And then lastly, to make the table descriptive, I'm going to use a dim names argument to indicate what are the names of the rows and the columns. So the rows are represented by what happened on the first free throw attempt. Either it is made or miss. I combine that together using the C function. Then the columns represent the second attempt. I'm going to combine it together. I'm going to combine together the made and missed again. Now I put all this in here into a list. A list is a special kind of way to put stuff together into an object of R. So you can see here I highlighted just that small segment of code inside of the array function, and look what we get. We get $sign first, so there's the first, and then we have the 2 levels made and missed. Similarly for second. So if I wanted to, I could create an object with that list. Oops, there we go. And if I did temp $sign first, I could just pull out what's represented as the rows. That $sign should look familiar, especially in Appendix A when I talk about working with data frames. You use a $sign to pull out particular variable names. Now, why is this syntax essentially the same? That's because a data frame is a special kind of list. And so that's why the syntax that you should be familiar with carries forward here. So let me go ahead and execute this segment of code here. And if I type c.table, there's our contingency table. I can do a variety of different things with this table. So if I say c.table left square bracket 1 comma 1 bracket excuse me, what this tells R is I want row 1, column 1. I want that numerical value. If I said c.table and I remove the column designation, I get just the row. And similarly, here's how I can get just the column itself. Why is this helpful? Well, let's say if I wanted to sum up those items in row 1, I could use the sum function, and I can then put c.table with just the one row in there, and that's how I get then the corresponding sum 285 that we've seen previously. There are other ways that one could do this. Let's say if I use the function called row sums. Notice I get the number of made first free throws and number of missed first free throws as well. So I'm just summing up the rows. Now, using that information, then what I like to be able to do is find, let's say, the estimated probability of a made second free throw given what happened on the first free throw attempt. So what I could do is take my c.table and actually divide it by those row sums. Look what, and put in an object called pi_hat.table. Look what happens. What R does, so c.table is a 2 by 2 array, and then row sums gives me 2 elements. What R does, it matches up this first row with every item that's in the, let me say that again. It matches up the first item here with what is in the first row of c.table. It matches what is in the second item, 53, with what is in the second row of c.table. So this is then what we have as a result. So the estimated probability of success, the estimated probability of having a made free throw, given the first free throw was made, is 0.88. The estimated probability of a missed second free throw, given that the first is made, is 0.119. Notice if I were to add these up, I get 1. Okay, let me get back to where we are in the notes. What's interesting here, if we take a look at this, notice the probability of success on that second free throw is actually a little bit higher if Larry Bird misses the first free throw rather than if he makes it. And this is kind of counterintuitive, at least for basketball fans, because at least going into this data originally, I always thought that, if you miss that first free throw, that will have a negative or detrimental effect on making the second free throw. But at least in this particular sample, the reverse seems to be the case. So maybe when Larry Bird misses that first free throw, he concentrates more on that second free throw, making sure that he's using the correct form when he's shooting. So that could be some explanation. We'll look more into this data as we go along in this section. Now, the last thing I want to talk about is that very often when you have data that can be summarized in a 2 by 2 table, you get the data first in an unsummarized manner. So let's say I have a data frame called all.data2. And if we look at the first 6 values in that data frame, this could represent the ordering of Larry Bird's free throw shooting. So the first pair of free throws, he made the first, made the second. The second pair, he made the first, missed the second, and so on. And so what we have here, if we were to look all through this, we have 338 rows of data representing the 338 pairs of free throws that were shot. Now this all.data2 is created in my corresponding program. You're not responsible, at least at this time, how the data comes about. In a later chapter, we'll talk about how we can create data in this format. But I just did this here because very often, again, the way that you get the data first in one of these situations is where you have these columns for your variables of interest. The first free throw attempt, the second free throw attempt, and now you need to create the contingency table. Here are 2 ways to do that. One could look at the table function that we've seen before, where all I do is I pull the first variable out of all.data2, I pull the second variable out, suppose I put the results into bird.table1 for the lack of a better name, and here's my contingency table. An alternative way to do this is to use what's called the xtabs function. What this corresponds to is, if you've heard of something called crosstabs or cross tabulations, that's where this name comes from. And the syntax is a lot different from what we have for table. First, I have an argument called formula. I say equal, and then I need to say tilde first plus second. Then I can say my data is in all.data2. Now, where does this kind of, maybe at first might think of weird syntax come from? Well, this is a standard syntax that people use when they want to, let's say, tell R, well, suppose I have a regression model. How do I want to denote it? And later, when we start looking at regression models in this class, we'll see, well, this is why this formula argument is set up in this way. For now, just use this syntax. So I put the results into bird.table2, and here's my exact contingency table that we had before. Okay, so that concludes this little subsection here that gives you some motivation for what we're going to be doing over the next set of notes, and also gives you a little bit of idea of how to work with a contingency table inside of R.